Welcome. With this video, we're going to continue discussing our algorithms for linked lists. Let's consider the ability to find specific nodes in the list and return a pointer to those specific nodes. There are various criteria that we can use to select the node. We can select the node by a specific value. For example, we can say, let's go look for where the value 8 is in the list. So if we were to do that, how would we proceed? We'd start with the first node. Its value is not 8, so we would move to the second node. Its value is not 8. Move to the third node. Upon observing that the value field is an 8, we break off the search. So we will stop when P is pointing to the node that contains 8. So what does the code for that look like? Well, the code is pretty simple. Even if you have an empty list, this code will do the trick. Because we start in our continuation. Notice that we are taking the standard traversal loop and we are adding an additional condition that will allow us to exit from the search if our criteria is met. So we're saying, and in C++, logical expressions are short-circuited. And that simply means if I have an AND operation, if the left operand is false, I do not attempt to do the right argument, the right operand. So if I reach the end of the list, I'm going to stop because this occurs first. If I have not reached the end of the list, I may stop because this occurs, okay, or this does not occur. So if we're looking for a specific value, we're given the value, let's call it key, and we will search until we find it. All right, let's go back to our search again. Suppose we want to look for nodes that are bigger than a specified value. So let's say we're going to search for a node, the first node whose value is bigger than 6. I start the search. This is not bigger than 6. I move to the next node. This is not bigger than 6. I move to the next node. This is bigger than 6. So we want to stop and remember where this node is. So what does the code for that look like? I hope you're going to see that the code really looks like the standard traversal with an additional condition being applied. So it looks exactly like we saw before, but this time, if the node value is less than or equal to the key that you're given, I changed the word here from key to big, then we keep moving. If the value in the node is bigger than the key, then we stop at that node. And if we stop there, the value of P will be appointed to that node that has a bigger value. All right. Now, lest you think we're just doing something with no purpose, suppose we wanted to build a sorted list. What would we have to do? Well, if I had the number 6 to add it to the list, I really need to reach the point where I say 6 goes before this node. All right. But in order to insert inside the list, we need 2 fingers. We need 2 pointers. We need to know what's going to be on the right of it, and we also need to know what's going to be on the left of it, because the insertion really takes place in between these nodes. Now, in class, we talked about a function that will give us this node. Do you recall what it was? This is a node. This is the successor of this node. This is a node. This is the predecessor of a node. So we really would like to be able to say, we have one finger on this node. We now need to find its predecessor. And so for that, we need to find the code for predecessor. And how does the predecessor work? Are you seeing this? This is the standard traversal loop, and we're just adding a condition so that we can exit early. Now, what's the condition? If I'm in node P and the next node happens to be the node that I want the successor for, I'm saying it the wrong way. If I'm in node P, then the successor node is in the next field. Whatever the next field points to is the successor. Whatever is being pointed to is the predecessor. Kind of getting confused here. So if I have one pointer pointing to the node I want to stop before I get to, this is how you do it. I'm not explaining this well. But the key point is I make my decision based upon not what's in the value field, but what's in the next field. So that if I were to do this, I would end up with two pointers. This is the predecessor. Let's call it Q for right now. This is P. And if I want to insert a 6, what would I do? I'd put 6 in here, and I'd have to do what? I'd have to put the 6 before this node, which means whatever this field is, I must point it, do that. And I must put the new node after this field, so I would have to reroute that. So that a way to do a sorted insert is to find the first value in the list that's bigger than the value you will insert, find its predecessor, and then insert the new node in between the predecessor and the bigger node. Okay, I think with that we're going to stop it.